One method of optimizing, that is to say, maximizing and minimizing, finding maximal and minimal solutions of an equation, is the use of Lagrange multipliers. This is particularly useful in the presence of a constraint. So what makes this method particularly useful? In order to do this, we set up a system called a Lagrangian. In this, in Lagrangian, f is what we want to maximize, where g minus c, g of x, y equals c, is our constraint. This is what constrains our solution. In order to start this, we take the partial derivative of each variable and also lambda, where lambda is an arbitrary variable that we do not define. In practice, however, it refers to the marginal increase of f with respect to a marginal increase in x or y. So, in order to solve this, we start with the partial derivatives. In this example, we are going to start with f of x comma y equals e to the x y plus times y plus 1, and with the constraint of g being 2xy equals 15. I chose this sample particularly because there was not an obvious easy solution to solve this with conventional methods. To write out the Lagrangian, we use this formula. So we get e to the x y plus 1 minus lambda 2xy minus 15, close bracket. Now we take the partial x derivative. This gives us e to the x y plus 1 minus 2 lambda y equals 0. The next partial derivative, L with respect to y, gives us e to the x minus 2 lambda x equals 0. Next, to solve this, we can include the constraint. The next derivative with respect to lambda gives us the constraint 2xy minus 15 equals 0. In order to solve this, we can first take these two equations. We can solve this for e to the x, which gives us e to the x equals 2 lambda x. If we substitute that into our first equation, we get 2 lambda x y plus 1 minus 2 lambda y equals 0. In this case, we can get rid of the lambda, divide both sides by lambda, and we're left with 2 x y plus 1 minus 2y equals 0. To simplify this, we can expand and divide both sides by 2 as well. Xy plus x minus y equals 0. Next, we can include our constraint. Okay, we can find a way to solve this. If we include the constraint, we can rewrite the constraint as xy equals 15 over 2. Or, better yet, we can solve this for x. Okay, this seems like an easy way, but leaves us with no clear resolution. So instead, I'm going to solve this for x, which gives us x equals 15 over 2, 1 over y. If I substitute this into our equation, we get 1 over 15 over 2, 1 over y times y, plus 15 over 2, 1 over y, minus y. This, as it is a difficult to solve problem. However, if we multiply both sides by y times y, we get the more solvable negative y squared plus 15 over 2 y plus 15 over 2 equals 0. This is solvable by use of the Pythagorean theorem. The quadratic equation. In this case, we can write out negative y squared plus 15 over 2 y plus 15 over 2 equals 0. We can set a equals minus 1, b equals 15 over 2, c equals 15 over 2. In that case, we set out the quadratic equation, which is minus b plus minus square root b squared minus 4ac over 2a. That will be our solutions to y. Notice, because of the plus minus, we'll get two solutions in this case. This is not typical, but certainly not unknown either. In this case, we will either have a minima and a maxima, or at least a saddle point. We need to decide which one is the appropriate one in this case. If we plug this into our calculators, we get solutions for x and for y. We get either for x we get 3117, 11883. That's 1.1. Also, we get 1.1883, 6.3117 after solving this equation. Now, there are ways to automatically tell which of these is the maxima. They are, however, complicated and mainly unnecessary, since in most cases it's simply easier to plug it into the equation and find out. For the bottom one, we get approximately 23.99. The top one gives us 1205.7. Clearly, this is the first one, the 1.18, 6.31 is the minima, and the 6.31, 1.188 is the maxima. This is a common and useful method for solving maximization in the presence of a constraint.